Hi friends. Welcome to my channel. Please like the video and subscribe to my channel if you like the video. Slide 1. In this video we are trying to solve a problem by using the concept of three-moment theorem. Before solving the problem, we should know that the concept of three-moment theorem is given by Clapreyon. And thus, this theorem is called Clapreyon's three-moment theorem. This method is used to analyze indeterminate structures like continuous beams. Analysis means finding unknown forces and moments. That means we are finding shear forces and bending moments in the given continuous beam to draw shear force diagram and bending moment diagram. Before going to analyze the problem, we should know what is the indeterminacy of the structure. A structure is called indeterminate structure only when the structure can't be analyzed by equilibrium equations alone. We need additional equations to analyze these type of structures. Slide 2. The equation given by Clapreyon to analyze continuous beam is shown here, that is MA times L1 by I1, plus MB times L1 by I1 plus L2 by I2, plus MC times L2 by I2 is equal to 6A1, X1, by L1 times I1, plus 6A2, X2, by L2 times I2. All the notations are shown here. Slide 3. For analyzing the given continuous beam we need to understand some basics. When a continuous beam is given for analysis, first thing is we should assume that all the internal supports are fixed supports and then write the support conditions for the both end supports. Here a continuous beam is given to analyze. Now, by seeing the given beam we can say that end support A is fixed, so, slope at A, that is theta A is equal to 0, and moment at A, that is MA is not equal to 0. Similarly end support D is also fixed. So, here theta D is equal to 0 and moment at D is not equal to 0. So, here we have to remember that moment at A is not equal to 0 and moment at D is also not equal to 0. By these inputs we are trying to solve the problem. Slide 4. Here this continuous beam A, B, C, D have three spans, AB, BC and CD. Span AB is of length 4 meters and is subjected to a point load of 80 kN at its center. Span BC is of length 5 meters and is subjected by an eccentric point load of 60 kN at a distance of 3 meters from B. Span CD is of length 6 meters and is subjected by an uniformly distributed load of 20 kN per meter throughout its span. In step 1 we are finding free end moments for all the three spans. Free end moment is the maximum moment calculated in the span by assuming both end supports of the span as simple supports. Here, span AB is loaded with point load at its center. For this case of simply supported beam, free end moment is equal to W times L by 4. That is 80 times 4 by 4, which gives MAB equals 80 kN meter. For span BC, loaded with eccentric point load, it's W times AB by L. It's 60 into 3 into 2 by 5, which gives MBC equals 72 kN meter. Similarly for span CD, loaded with UDL over its entire span, it's WL square by 8, means 20 into 6 square by 8, gives MCD equals 90 kN meter. This is the end of step 1 in which we have calculated free end moment for every span, AB, BC and CD separately. Slide 5. Now in the second step we are drawing the free end moment diagrams for every span separately. AB is supported by a point load at center, so we will get an isosceles triangle, as shown in the figure. Then span BC is supported by an eccentric point load, so we get a triangle as shown in the figure. Finally span CD is supported by UDL over entire span. So, it's a symmetric parabola as shown in the figure. The vertex of triangle in span AB will have an ordinate of its free bending moment equals to 80 kN meter. Similarly, the vertex of triangle in span BC also will have an ordinate of its free bending moment equals to 72 kN meter. And the maximum ordinate of parabola in span CD is 90 kN meters. As shown in the figure. This total figure represents the free bending moment diagram of given continuous beam A, B, C, D. Now step 3, in this step we are going to calculate the areas of all the free bending moment diagrams. For span AB, area of free bending moment diagram is half times base and height, as it is a triangle. For span BC, area of free bending moment diagram is also half times base and height, as it is again a triangle. Similarly, for span CD, area of free bending moment diagram is 2/3 times base and height, as it is the area under parabola. Here, the area of free bending moment diagram for span AB comes out to be 160 square units. And the area of free bending moment diagram for span BC comes out to be 180 square units. Finally, the area of free bending moment diagram for span CD comes out to be 360 square units. This is our step 3. Slide 6. Further, in our step 4 we are plotting the centroid of each free bending moment diagram from both ends within their span. For span AB, centroid lies at a distance of its half span from either side as the figure is symmetric. For span BC, centroid does not lie at its center as the figure is not symmetric. So, for this type of figure, we know centroid lies at a distance of L plus A by 3 from left support and L plus B by 3 from its right support. Finally, for span CD, centroid lies at a distance of its half span from either side as the figure is again symmetric. The values of centroid are plotted on the figure shown separately from both ends. This is the end of step 4. Slide 7. Step 5. In this step we are applying the 3-moment equation for the considered span ABC. The 3-moment equation becomes MAL1 plus 2MB times L1 plus L2 plus MCL3 is equals to 6A1 x1 by L1 plus 6A2 x2 by L2. Considering span AB as 1 and BC as 2, we are substituting all the known values in the equation. Now, the equation becomes 4 times MA plus 2MB times 4 plus 5 plus MC times 5 equals to 6 times 160 times 2 divided by 4 plus 6 times 180 times 2.33 divided by 5. That is equals to 4 times MA plus 18 times MB plus 5 times MC equals to 983.28. Where x1 is the distance of centroid of first figure from A and x2 is the distance of centroid of second figure from C. This is our equation 1. Slide 8. Now, consider span BCD. The 3-moment equation becomes MB times L1 plus 2MC times L1 plus L2 plus MD times L3 is equals to 6A 1x1 by L1 plus 6A 2x2 by L2. Considering span BC as 1 and CD as 2, we are substituting all the known values in the equation. Now, the equation becomes 5 times MB plus 2MC times 5 plus 6 plus MD times 6 equals to 6 times 180 times 2.67 divided by 5 plus 6 times 360 times 3 divided by 6. Here, x1 is the distance of centroid of first figure from B and x2 is the distance of centroid of second figure from D. So the final equation becomes 5 times MB plus 22 times MC plus 6 times MD equals to 6 times 180 times 2.67 divided by 5 plus 6 times 360 times 3 divided by 6. That is equals to 5 times MB plus 22 times MC equals to 1656.72. This is our equation 2. Slide 9. Here, we have MA, MB, MC and MD as our unknowns. But we have only 2 equations. So we can't solve these 4 unknowns by 2 equations. To solve 4 unknowns we need 4 equations. For that we need 2 additional equations. Now, to generate one additional equation, we are considering a zero span AA dash towards A, as shown in the figure. Now applying 3-moment equation to span A dash AB. The equation becomes MA dash times L naught plus 2 meters A times L naught plus L1 plus MB times L1 is equals to 6A naught x naught by L naught plus 6A 1x1 by L1. Considering span A dash A as 1 and AB as 2, we are substituting all the known values in the equation. Now, the equation becomes 0 times MA dash plus 2 meters A times 0 plus 4 plus MB times 4 equals to 6 times 0 times 0 divided by 0 plus 6 times 160 times 2 divided by 4. Here, x0 is the distance of centroid of first figure from A dash and x1 is the distance of centroid of second figure from B. We know moment at A dash is equal to 0, L0 is equal to 0 and also A0 is also 0. So the final equation becomes 8 times MA plus 4 times MB equals to 6 times 160 times 2 divided by 4. That is equals to 8 times MA plus 4 times MB equals to 480. This is our equation 3. Slide 10. Now, to generate another additional equation, we are considering a zero span DD dash towards D, as shown in the figure. Now applying 3-moment equation to span C, D, D dash. the equation becomes mc times L1 plus 2 meters d times L1 plus L2 plus md dash times L2 is equals to 6a 1x1 by L1 plus 6a 2x2 by L2. Considering span CD as 1 and dd dash as 2. We are substituting all the known values in the equation. Now, the equation becomes 6 times mc plus 2 meters d times 6 plus 0 plus md dash times 0 equals to 6 times 360 times 3 divided by 6 plus 6 times 0 times 0 divided by 0. Here x1 is the distance of centroid of first figure from C and x2 is the distance of centroid of second figure from D dash. We know moment at D dash is equal to 0, L2 is equal to 0 and also L2 is also 0. So the final equation becomes 6 times mc plus 12 times md equals to 6 times 360 times 3 divided by 6. That is equals to 6 times mc plus 12 times md equals to 1080. This is our equation 4. Slide 11. Now we have 4 equations and 4 unknowns. So, we can solve the unknowns. By solving above 4 equations we get the values of final moments as MA equals 44.69 kilonewtons meter. MB equals 30.60 kilonewtons meter. MC equals 50.72 kilonewtons meter. MD equals 64.63 kilonewtons meter. Slide 12. From these calculated final moments we are drawing final bending moment diagram. For drawing final bending moment diagram, first we should draw free bending moment diagram. And on that we have to plot our final moments values. Further joining them we will get our final bending moment diagram of given continuous beam. Slide 13. Thank you for watching. Hope you like the video. Please do like the video and subscribe to the channel.